Good afternoon, everyone, and thank you for joining us. We are Team Synapse from Bangladesh University of Engineering and Technology, and we are excited to present our submission to this year's IEEE Vision and Image Processing Cup. Let's take a quick look at what we'll be covering. We'll start with the problem statement, move on to our pilot experiments, and then discuss our findings and methods. After that, we will share some alternate strategies we explored, and finally end with our results. First, let's talk about the problem we are addressing. I know the organizers have probably introduced the problem already, so I will move through this section fairly quickly. In short, the task was to detect biomarkers from ophthalmic coherence tomography scans or OCT scans. The competition dataset was the OLIVES dataset for OLIVES research team at Georgia Tech. The trained dataset had around 9,000 images from 96 patients, while there were two test datasets for the two phases of the competition, each from totally different patients. These are the biomarkers we had to detect. I'm not going to go over them one by one. However, notice that one of the columns type has been intentionally left empty. That's one of our core findings for this problem, and I will circle back to it in later sections. Moving on. The training dataset also included some clinical labels which we had the option to use. Between them, the first one, BCVA, is not something that's usually determined from OCT scans. Doctors generally use a Snellen chart like this one to determine BCVA and prescribe corrected lenses to patients. We also found that embeddings, neither of the images nor of the biomarkers had any easy to notice patterns. However, if we plot the correlation between the different biomarkers, we can see that the train set and the test set are quite different. And this domain shift definitely becomes important later on. Moving on to our pilot experiments, we experimented sensor processing units and added attention to them. Here are some of the images from phase 1 and phase 2 of the competition. As you can see, the second data set was already pre-transformed, so we had to deal with that. In phase 1, we kept augmentations pretty simple. Random cropping, flipping, and color jitter are the main ones we used, and this is how the images look like after augmentation. And in the second phase, we added perspective shift to match the second training dataset, the second test dataset, and this is what the images looked after augmentation. We used 5-fold cross-validation for training all of our models. This basically involves partitioning the training data in 5 sets, training on 4 of them, and evaluating on the remaining 1. After each training session, we infer on the test dataset and save the model outputs. Later, we combine the predictions from each split with a simple average. Another important thing to note is that all F1 scores I'm going to show from now on are from the first test dataset. We were given access to those labels after the first phase. Before that, we could only estimate our model performance based on leaderboard scores and validation set. Also, all of our scores are going to be averaged across all images, which represents the generalization ability of our models. We also have a section in our report in which we analyze our patient-wise F1 scores. We used Kaggle's TPU instances for rapid experimentations. Typically, testing a model took about 1 or 2 hours. However, the caveat is that it does not support all models. So, how should we go about selecting models? ImageNet is arguably one of the most widely used datasets in computer vision, and we wanted to find out how does it correlate with the task at hand, biomarker detection. So this is a scatter plot that shows the relationship between F1 scores and the ImageNet accuracy. The radius denotes the model size. As you can see, ImageNet is not a good indicator for biomarker detection. As a result, we couldn't simply take the best performing ImageNet model, train it, and call it a day. So in our pilot experiments, the best model we found was Inception Recent version 2, quite an old model from 2017, and it has only about 55 million parameters. Interestingly, Inception version 3 with just 24 million parameters was the second best performing model, and the scores were very close. So what's happening here? Why does Inception beat out larger models that do way better on ImageNet? We actually do have some intuition about this. If we go back to the very first introduction of the Inception network from way back in 2014, we can see that Inception uses kernels of different sizes in parallel. The authors mentioned this in the paper. We hypothesize that this multi-scale processing is the key reason why Inception does so well. As to why, we'll get back to it in later sections. There is one final thing we tried as a part of the pilot experiments, adding attention. Following some notable literature in medical imaging, we added convolutional block attention, or CBAMs, to our best Inception model. We kept things pretty light and added CBAM layers to only 3 places inside the Inception resonant model. This increased the parameter by less than 0.5%, but it did absolute wonders for our model performance. So with a little bit of attention, we get a solid improvement in our F1 scores. Naturally, we want to find out where this performance gain is coming from. If we calculate the F1 scores by biomarkers, we can see the improvement mainly comes from 3 biomarkers. Why? So that's what I'm going to address in this section, which we call divide and conquer. Here are the 3 biomarkers where adding attention, CBAM layers really helped, and they do have something in common. They appear quote-unquote local, as in we, or rather a trained ophthalmologist, can detect them by looking at the subsection of the image. As for the other 3 biomarkers, one needs a more expansive view. We believe this is the main reason why Inception models in our pilot experiments were doing so well. Their multi-scale architecture might be better at handling local and global biomarkers separately, but in parallel. Finally, we categorize biomarkers as either local or global based on their spatial extent. As for the 5th biomarker, diabetic macular edema, it falls somewhere in between. We actually consulted an ophthalmologist about our classification method, and we were informed that sometimes doctors cannot reliably detect edema from just a slice of the image. This is kind of expected, honestly. Biomarkers, as with most things in medicine, are a complex topic after all, and don't have clean classifications most of the time. Now, if we go back to the comparison of Inception with and without attention, we can clearly see the improvement stems mainly from the local biomarkers. So just a quick disclaimer, our classification of biomarkers by spatial extent is in no way a medical thing, but it did help us in selecting models and to reason about their performance. For more extensive experiments, we finally move on to GPUs, which are slower but support all frameworks. Each model typically takes about 6 to 12 hours to run, so we have to be really selective regarding which models to try out. The first model we tried was the original vision transformers introduced in 2020. It scored around 0.7, which is pretty close to Inception models. So it looks like attention is not all we need. The best model, at least ImageNet score-wise, with both convolution and attention we found was MaxVit. Of course, there are many other models like this. If I remember correctly, the Swin transformers were the first to include convolutions. However, I want to remind you that with GPUs, each run takes more than 6 hours, and we couldn't simply try them all. So MaxVit scores about 0.718, handily beating both vision transformers and Inception. As good as MaxVit is, we thought there was room for improvement. MaxVit uses sparse attention mechanism, which is better for scaling. Since scaling is not something we're focusing on in this competition, we wanted to try something that has true attention. The original vision transformer does have that, but it's from 2020 and it's getting a little outdated. We found that the best plain vision transformer model currently is EVA 2, introduced this year. It has some minor architectural changes from the normal vision transformer, but the main reason for its stellar performance is probably knowledge distillation from a much larger 1 billion parameter model. And this model is smaller than MaxVit as well, about 2/3 the size and the same accuracy on ImageNet. So EVA score is about 0.709, not bad. But if you look at the F1 scores by biomarkers, we can see that MaxFit does better on local biomarkers and EVA does better on global biomarkers. Naturally, we want the best of both worlds. So doing a simple average of their outputs, we ensemble MaxFit and EVA, achieving our highest F1 score so far. Just to be clear, all these F1 scores were averaged across all images. We have the patient-wise F1 scores in our report. And this ensemble is our final submission to this year's Vision and Image Processing Hub. I'm almost done. I want to take a minute and go over some things we tried, but that didn't quite work out. I'm going to keep this short, but we do go into more detail on this and error analysis in our report. As a reminder, we had two clinical labels beside the biomarkers. If you take a look at the correlation matrix, the labels do have some correlation with the biomarkers. We also had about 78,000 images without any biomarker labeling. So we thought of some ways to use them. Motivated by some literature, the first thing we tried was contrasting learning on CST. Unfortunately, that did not help, at least on the inception model. We tried pre-training to predict the labels. No luck. How about training to predict both the biomarkers and the labels together? Still no improvement. And finally, we tried pseudo-training where we tried to increase the trained dataset with unlabeled data, but that actually harmed performance by a lot. All of these attempts were on the inception model due to computational constraints. That does not mean they can't work on other models, especially large transformers that can store a lot of knowledge implicitly. It might be worthwhile to try them and some other transformer-specific things on vision transformers, but we leave those for future work. Here's the leaderboard for phase 2 of the competition. I believe these are patient-wise averages, hence they are quite a bit higher than the 0.724 we got averaged across all images. As you can see, our team ranked highly, about 4% better than the second best solution. That's about it for our presentation. We'd like to thank the IEEE Signal Processing Society, the Olives research team from Georgia Tech, the honorable judges and organizers. We would also like to thank Dr. Rezwan, who corroborated our findings regarding classifying biomarkers. We have the report hosted on the internet at this link. It's also in the QR code if anybody wants to check it out. We do plan on releasing our code after the competition, and in the meantime, please feel free to email me as well. Thank you for your attention, and we are open to questions.